Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we got no problem. Because today we're going to talk about something really cool, collisions, and how we can calculate what happens after a collision. Bang, bang, collisions. Turns out there's two kinds of collisions. First one is an inelastic collision, and the other is an elastic collision. An inelastic collision, we'll just call it a sticky collision. When something strikes something else, they stick together. And then an elastic one is a bouncy one. That means that they strike each other and then they bounce off each other. Now, the reality is there's no such thing as a completely elastic collision because some energy is always imparted. But there are some situations where you have where the collision, there is no energy lost to heat and sound and all that kind of stuff. Like an example would be a bouncy ball. And actually, one thing that does follow this very closely is atoms in a gas. If you remember back to chemistry class, you learned about gases. So in this room, I'm on the Earth, and there's little tiny gas particles. And those little gas particles, they run into each other, and they really run into each other very elastically so that there's no energy loss because they're so small in the space of the air. So things like bouncy balls, etc. We're going to mostly spend our time with elastic collisions. Well, we're going to talk about inelastic collisions. In this video, we're going to focus on inelastic or sticky collisions, and the next video will be elastic. Now, we want to say one other thing. In inelastic collisions, momentum is conserved. Momentum. I'm misspelling. It's conserved. And, of course, momentum is conserved here. Here, though, there's the contrast. Kinetic energy is not conserved in an inelastic collision, but over here, kinetic energy is conserved. And this implication is going to be huge when we do problems in the next video. But let's talk about these. So we don't need to worry about kinetic energy here. It's all just a momentum problem. Let's flick to the examples. So here we have the train example here. So we've got two trains, and when they hit each other, they stick together, and they have the same mass. So this is going to be like this. M1V1 plus M2V2 equals M1V1 plus M2V2. Sometimes we'll put a prime on these, meaning after the fact or secondarily. So in this case, right, we've got only one in motion, the first car, and it's M1. And by the way, all the M's are the same, so we can say M times, and what is it, 10 meters per second. And this V is 0, so this term drops off. So we can say that's equal to, now what's going to happen when they're elastic or inelastic? What's going to happen is that these guys are going to combine. So it's going to be one full term. So we're going to just say, if you will, M1 plus M2 times V. We want to find the velocity. Now remember though, each of these masses are the same, so we can say M times 10 is equal to 2M times V. Because it's the same mass, the M's cancel, and so we divide both sides by 2, so the velocity of them together will be 10 divided by 2, or 5 meters per second. Now hopefully that makes sense. If they collide and they keep going, he's going to transfer his momentum, and it's going to be halfway, and that makes sense that it's 5. That was a relatively easy problem because they had the same masses. But this next one, a more complex collision problem, as you can see, is the two players, so football players. And they're going to collide with each other. So our first guy has a mass of 100 kilograms, and he's moving at 3.75 meters per second. And the second guy is a bigger cat, and his mass is 120 kilograms. And he's moving faster, 4.1 meters per second, and he's moving in the opposite direction. What is the net movement? Because they're going to stick when they hit each other. So we know we can do MV and MV. We're going to find each of their MVs. You'll see it's vectorial. So let's just do this. 100 times, so M, 100 times 3.75. That's going to be 375. And this will be 120 times 4.1, and that becomes 492 kilograms meter per second. So let's think about this. Momentum, what's the net momentum when they strike? this guy, it's going to be backwards in this direction, and the amount of momentum will be 492 minus 375. Or add them, if this is negative, it'd be 375 plus negative 492, and I get the change in momentum to be, if you will, negative 117. That's the difference between these two, kilogram meter per second. But the question is, what's their final velocity? Because they stick. So we can set that equal to the final condition, which will be mv. Well, their final m, though, is going to be 100 and 120, because now their mass is bigger, so that's going to be equal to 220 times v. So we divide both sides by 220, because this is negative. We get v to be negative 0.53 meters per second. So they're going to be, this guy's going to drive this guy backwards, and they're going to be moving, at least at the beginning, at negative 0.53 meters per second. And our last example now gets kind of more vectoral, SOHCAHTOA-esque. So let's see if we can figure this out. So we've got a diagram right here. We're going to have a car, a sports car, and a car, and they're going to have a collision. All right, so what we've got going on is, what do we know? We've got an x, right? The p initial in the x direction, right, is going to be equal to the p final in the x direction. All right, so that's the x direction. We've got an x and we've got a y. So let's think this through. So we can say that this is mi vi is equal to, now the final, because now in the final momentum we're going to have two cars. M1 plus M2, that's the two cars, right, times the final. Now let's think of this. You're looking at the question now. Notice that when they strike each other, they careen off at a 61-degree angle. Let's draw our angle here. So this is 61 degrees when they're stuck together. So we've got a little SOHCAHTOA stuff going to be done. And what we want to do is we want to figure out what their final velocity equals off at the 61-degree angle. But what we can do is we know that the velocity final, is going to be, we know the x number is, this is 16 meters per second initially, and you can't just do it, it's 16 meters per second, the masses are going to play a role. So what I want to do is I want to find out what this number is, but we can say that using cosine, this is adjacent over hypotenuse, cos of 61 times v initial is going to be equal to this number. So that's the v here, right? So I can say v initial times cos of 61. Does that make sense? Now we know what these m's are. M1 is 950, right? V initial is 16 meters per second from here, right? Equals the sum total of these, I'll just write it out, 950 plus 1300 times V initial cos, actually this is not initial, pardon me, this would be V final, cos of 61. And then we do the math. I'm not going to do the math here. You can solve for V final, and you get 13.9 meters per second. You got one variable, one unknown. You solve this mathematical problem. Now you may need to spend some time to figure out how to do that. Now you'll say, Mr. Bergmann, why did you do the y version? Guess what? We can do the exact same thing with the y. They have to agree, because if you've got 61 degrees and we know the final number, I didn't ask you to solve for the angle, which I might have done. It's going to be the same idea, except what's going to happen? Well, I'll just write it out. I solved it. You're going to say mi, instead of, this is x, if you will, miy, so I said 1300, that's the mass of the sports car times 21, he was moving faster, is equal to 950 plus 1300. Same thing we do there, times v final. Now in this case, this isn't 16, this is 21, and now we're going to do opposite over hypotenuse, so I'd say sine of 61. And then we do the math, and you know what we get? V final to be 13.9 meters per second. So more problematic problem, because now we have to bring in the trigonometric things. Houston, collisions are cool. And inelastic collisions, the sticky collisions Can be complex, but it's just simple trig. We'll do some of these in class because I know you're still struggling with it, but that's okay. We got time. You're going to learn because you're smart. We'll see you there.